What is a turbo? How do we put one on a car if it never came with one? And how is 3D printing going to help with that anyway?
Copy the same old sound, painted our lives. But could you tell me what it is that I'm missing? Oh, keep that mind tucked in your prison. These prisms swell.
Yeah, or is it better if we overflow it? And birth poets, young kings set to overthrow it. Spread wings like what RD was just a scribble on some dotted paper. You hear things, now we major, huh? Long removed from the youth that I remain once.
Atmospheric pressure, as you might assume, is the pressure of our atmosphere. It's measured as the weight of the air all around us being pulled down towards the surface via gravity. Therefore, the higher you are in the atmosphere, say on a mountain, the less air pressure there is, and conversely, the lower you are, the more air pressure, usually referenced as height above sea level. That's why you'll often see mountain climbers with oxygen tanks and other support. There's less available oxygen in the air that they can breathe in. Fresh air around the engine is at atmospheric pressure. As a general rule, this is assumed to be 14.7 psi or 1 bar, or 1 atmosphere. As the piston moves down inside the cylinder in its intake stroke, it creates a vacuum, a pressure difference, and causes suction. Like this syringe pulling water, it works in the same way. Don't confuse this with volume. Yes, we can bore cylinders, add bigger pistons, increase the stroke length, but the vacuum we can create on the intake stroke to suck air in will not be greater than atmospheric pressure. Okay, so we've sucked the air in, compression stroke, ignition/power stroke, then exhaust stroke, where we push the burnt, used air out of the cylinder. This then flows down the exhaust and out the back of the car. It's essentially spent energy that we're now discarding. But if we have a turbo on the car, or if we choose to add one, we can harness this exhaust gas and use it to help us increase performance.
Would you like to know more?
This is a CT12A turbo off a 1JZ engine. Incidentally, the 1J actually comes as a twin turbo, but one turbo at a time. Don't worry about these oil and water lines for now. Let's just start with the basics. Very simply, let's think of a turbo as having 3 parts: a compressor housing, an exhaust housing, and a core. Exhaust gases flow in through this inlet here on the exhaust housing and are pushed past this wheel, which causes it to spin. As the wheel is spinning, the exhaust gas is rushing past it. The faster the flow of exhaust gas from the engine, the faster the wheel will spin. This exhaust gas now exits through the rear housing here and continues on down the exhaust as it normally would in a non-turbocharged car. So the engine's running, exhaust is flowing, this wheel is spinning, and it's attached to a shaft that is also therefore spinning. The shaft continues on through the core of the turbo and into the compressor housing, where there's another wheel attached on this end. Because both wheels are attached to the same shaft, the spinning of the exhaust wheel, or turbine, causes the compressor wheel on the other end of the shaft to also spin. Except rather than forcing air out of the turbo like in the turbine wheel, it sucks air in. Once this air is sucked in, the shape of the blade forces the air into a smaller and smaller space, thus squeezing or compressing the air. This outlet from the compressor housing is attached to our engine's intake manifold. And now we're back to where we were at the start, except instead of atmospheric pressure, we have our increased, boosted, or boost pressure. Finally, we need a way to control this pressure being added, and we do that via a wastegate. As you might imagine, it is a gate for waste. Once we've achieved our desired boost pressure, we want to maintain that and bypass the turbine with any excess exhaust gases. We can bench test this function by giving it some pressure. I believe factory pressure is around 8 psi. We need to be careful with the pressure we apply here. We don't want to destroy the diaphragm inside the wastegate. We can increase the pressure needed to open the wastegate with something like a boost T, but that's a discussion for another day. So that's a very simplistic explanation of the system. Let's leave it there for now. Naturally, there's a little more involved than just bolting on a turbo and sending it, so let's look at how we might do that. I spoke in previous videos about knowing our minimum bounds or requirements for a project, and for this one, that's going to be how we incorporate the turbo into the exhaust system, because no matter what, that is a requirement. Before we get too far ahead of ourselves though, let's mock up our dummy engine. I've got my old 5K engine on this stand here, which will be perfect for the mock-up, but we need to have a few things on there that are missing. One of those being the starter motor I just stole off the KE70. However, you might know that a starter is held in place via the gearbox, which you might also notice is not attached. So I'm going to put the sandwich plate back on and bolt through that. If you're yet to sign up on my website, this adjuster knob I designed is available free to download and print yourself at home. I'll talk a bit more about that later. So this is a locating dowel for the manifolds. There's meant to be two, and then this is one of the studs for securing the manifolds. I'm eventually going to replace those dowels with two more studs, I think, but for now, seeing as we're here, I'm going to remove the remaining stud and clean out the threads before fitting some new, slightly longer studs. Obviously not critical for the mock-up, but we might as well test a few things at once. You can see this is obviously a threaded stud hole, and then this one is where the other dowel would go. Should be pretty easy to drill and tap to size, but I'll do that at a later date on the mill when I clean up the rest of it. Also, I should probably ideally be using a thread chaser here instead of a tap. However, this one is kind of blunt and the threads don't really look too damaged, just full of gunk, so I'll take my chances. The reason you'd use a chaser rather than a tap is that you risk cutting away material with a tap and potentially weakening your threaded hole. This time capsule doesn't look a day over 50, although its time spent as a paddock basher is beginning to show. Someone has bypassed the threads using a smaller bolt and nut to go through the hole, so we'll get rid of that and attempt to run a tap through here as well. This is the solenoid for the starter motor. It takes power straight from the battery and sends it to the motor, causing it to spin. This little tab here is the momentary power for the starter that starts the whole process. I think I know the answer, but let's give this a test. In contrast to most new things, if we pulled one apart, we might be able to get it working again.
Would you like to know more?
Oh wow.
Actually useful. You can do things with these.
You can. You can keep them if you want.
I am going to keep them.
Oh, you left one. Oh, we need one. We're allowed to use one.
If you like.
I do like. Huh?
This is wrong bolt.
Talk to Jaden.
This is an imperial thread.
Talk to Jaden. Jaden, can you read or no? You know what else I hate? Red Hot Chili Peppers. I did say we'd talk a bit more about the disco, but one tangent at a time. So this is our solenoid, and it has 12 volts directly from the battery. This is why we disconnected our battery at the start of this process. Then we have this other terminal, and that connects the solenoid to the motor. We bridge these two posts inside the solenoid by turning the key and sending power to this terminal here. Now that we've got our solenoid body off, we can see how it's hooked onto this lever here. In our drawing, it looks like this. Alright, let's get this cap off and see what we're looking at. Okay, so you just saw us desolder this pin here, which is the power for the solenoid. This receives power when we turn the key, or in the case of the setup on my KE70, when I flip the momentary switch. And as a result, when the solenoid is energized, this contact is pulled up to meet the terminals. It bridges the two and thus energizes the starter motor. Before we go further, we can see the issue here. These contacts are burnt and making a poor connection. You can see the surface roughness on them, and if we were to exaggerate it in a drawing, it would currently look something like this. This is the clicking sound we heard before. The solenoid is being activated and pulling the contact to meet the terminals, but power is not consistently being transferred to the starter motor. So we're going to spin these posts around to use the fresh side of the terminals, and we're also going to dress them with a file just to remove that surface layer of oxidation and make sure we've got the best connection possible. We'll do the same on the solenoid bridging contact as well. Now it's time to put it back together. We'll check the resistance of the solenoid. About 1 to 2 ohms is what we're looking for. Now as we reassemble, we'll make sure we attach the hook back onto the lever of the motor, which works like this when the solenoid is activated. So we looked at the solenoid internals, but what's happening inside the motor? So we send power to the solenoid, it gets pulled up and bridges power from the battery power terminal across to the motor, which causes the shaft and the attached starter gear to spin. At the same time, the lever attached to the solenoid shaft pulls the starter gear outside the housing, which, when installed, would make contact with the engine flywheel and cause the engine to turn over. But Ryan, why does sending power to the solenoid cause it to get pulled up to bridge those contacts?
Would you like to know more? Hello, Clarice.
Cool, huh? If you watched my previous video where I discussed the function of a relay, which is also an electromagnet, the principle is the same here. A copper coil is energized when we send power to the solenoid, and it creates a magnetic field which pulls the shaft up in the same way that we see with this armature on the relay here.
Would you like to know more?
Wow, that's 4 times in a row. What are the chances? Alright, I said we'd talk about the disco, so for those of you who asked, here we go. I'm about to regurgitate a whole bunch of info. First thing you might notice is this filter filtering itself. Those white flakes are paint from the filter, apparently. It's a modified 3.9, which is actually a 4 litre. This is a non-cross bolt main block, which has a larger crankshaft and has been bored out to 5 litres. Custom camshaft and heads, Commodore 5 litre Bosch style distributor, larger AFM with an adapter to change the signal to the standard ECU. It was tuned on a Rover gauge, which I'm told Land Rover nerds will know what that is. It also has a fully electronic P38 4HP 24 long case with CompuShift. Torsen Eaton TrueTrack front diff, AxiDrive axles, Eaton Detroit in the back, both auto lockers. Angelo's apparently not a fan of air lockers as they have a tendency to break. Custom transfer case with reinforced housing. Not sure exactly what power it makes, but we estimate it's triple what it did from the factory, which isn't saying much. But to put a number on it, something like 250 horsepower. Look at all that space.
So many activities! Do step class. It's making my head spin how many activities we can do.
It's a 1994 model, changeover from the early 2-doors to the later style dash. Good body with a good engine, Disco 2 headlights with the black inserts.
I never asked you. Yeah. You like guacamole?
Wow, that was some tangent. Now we've got this nice clean starter, we'll get it bolted up, and we can also see another consideration of our setup. The starters on the K engines can vary quite a bit. I'm pretty sure there's at least 3 different types, and the solenoid position on this starter is much further from the block than my 5K starter. It will allow us to design for the worst case scenario, but it's something to think about in terms of compatibility with other setups. Next is this EGR port, which we're going to need to block as I won't be running it. However, I don't really want to modify this one if I don't have to. I want to replace it with a plug. I'm pretty sure these are M28 by 1.5 threads, but we'll come back to it later. This is another annoying feature of this manifold. It actually seals against the factory intake, and as you might be able to see, it has a tendency to leak. I'm sure this will be especially so when boosted. At the very least, I would like to surface this on the mill. Ideally, I would weld this up, but we'll see how we go. Finally, this outlet seals via a circular exhaust flange gasket. These generally seal very well, however when compressed, it eats into the exhaust path, creating a mild obstruction. Something we need to remember though is that this is still a tiny little pushrod 4-cylinder. Yes, it needs all the help it can get, but let's not get hung up on too many things right now. I might modify another manifold at a later date to compare performance to, maybe. Okay, so we're going with the Schedule 40 pipe like we discussed, but we can already see an issue. We know we're going to have to be pretty precise with the positioning to get the turbo to fit down here, and the idea of holding, taping, tacking, and adjusting these pipes is reminding me of a particular meme. So, what are we going to do? Well, I've chosen 2-inch, short radius, 90-degree elbows from the manifold, a 2-inch to 1 1/4 inch reducer, and a 1 1/4 90-degree elbow from there. Also short radius. I don't know how many of each and what configuration yet, but I'm going to start here. And now I'm going to do what I often do and make a CAD model. But I'm also going to do something that I don't often do, and that is make these files available for you to download and print yourself at home. These are available on the silver tier of the website, along with a whole bunch of other files, and there is a lot more to come. Alright, to CAD. You could take your measurements off the physical item, obviously, or you could also cross-reference with the spec sheet if there's one available. I said earlier that I'd already chosen Schedule 40.
Why? We don't have.
It's pretty tried and true for this application, but what does Schedule 40 actually mean? Let's keep it really brief and simple. In this example, a 2-inch elbow is the nominal pipe size, NPS, or nominal bore. It's the same thing. It indicates nominally the inside diameter of the pipe. However, this ID will change depending on the wall thickness that we choose. 2-inch pipe has a constant outside diameter of 60.3 millimeters, but then we can see that the schedule of the pipe indicates different wall thicknesses. Therefore, we can also see that the thicker the wall, the less space left inside the pipe, hence a smaller ID. The schedule is actually derived from a formula, but basically it's the wall thickness and also indicates the pressure that a pipe can handle. More schedule, more stronger. Cool. So I want these designs to be modular so that they can all be mixed and matched together, which will allow me to try different configurations. So I've made a little male and female boss on each end, as well as provisions for a bolt and nut on each. Then I also added some degree marks, which will come into play a bit later, but as you can imagine, this will allow me to reference the angles I decide on and transfer the design to the real components, jig, and weld it up. Next we've got the flanges for both the exhaust and the turbo. I measured these up in the ways I've described previously and a little trial and error to ensure they fit appropriately. Except, we're going to see another example of why we don't just trust the models we download or are given from anyone but the OEM. Sometimes even then. This CT12A model is actually not mine. I'm sorry I can't reference whose it is, as it was given to me a long time ago, but I've been using it temporarily until I make my own from a 3D scan. I'm not here to trash this person's effort, it may have been fit for their purpose, but currently not mine. So luckily I'm checking it now, rather than making a whole bunch of parts that won't actually fit. I've now tweaked all the components so that they match the physical versions, and I've also gone ahead and made some extra bits and pieces that I'm going to need later. As I mentioned, I'm not sure exactly how it's going to best sit together, and rather than play around with it any further in CAD, I think I've got more than enough to get going with a physical mock-up. I've also made a 45 degree of the 2-inch elbow because I got a feeling that I'm going to need that, and once I've tested the setup, it's very possible that I'll need some other, more specific angles as well, but we'll see how we go. Alright, the good stuff. Let's actually start mocking some things up. Immediately I know this stud is going to interfere. I'm using these ones for the mock-up, but I'll fit some shorter ones when they arrive. I still might need to end up putting a little piece of straight section here to space it out of the way, but let's just remove the stud for now while we play around with some ideas. Honestly, I'm a little worried because literally everything is working exactly how I wanted it to in my head, so I'm on the lookout for flying pigs. In the meantime though, I'm going to play around with some ideas and configurations to see what I can come up with. All these degree marks are also working perfectly and will allow me to translate them to the final parts pretty easily, I reckon. They're marked in 11.25 degree increments, which is more than accurate enough for this project. Obviously, if they end up between markers, I can still get them pretty close with some approximations. One more thing before I bring the turbo over here though is another obstruction we need to avoid, the engine mount. Another thing we need to think about is the oil drain on the turbo. If we don't have this high enough so that it can easily gravity drain back into the sump, we risk backing up the oil and preventing it from circulating. This would be bad. There are solutions for that, such as an oil scavenge pump, but we're going for sleek and simple, if possible, so we're going to try and avoid that. After some playing around, I'm liking the look of this position, however this straight reducer is giving us some unnecessary height in this configuration, which we'd have to overcome with a long straight piece to get the turbo mounted lower. Let's instead try 2 more 90 degree 2-inch pieces first, then to the reducer. Now I'm actually going to be mounting this in a different position to the factory setup. Sorry for the poor example images, they're hard to find, but basically I'm going to need a clock or twist the turbo housings in order to have it mount in my desired position. You can see that these are a V-band connection from the core to the turbine housing, and in theory I should just be able to spin them together like this, but I suspect there's a whole bunch of soot and gunk backed up in there holding them in place, so I'm going to have to separate them. These CT12s have a ceramic turbine wheel, which I plan to try changing at a later date, but that's beyond the scope of this video. This should give you a better indication of what I was talking about regarding clocking the housings. Let's leave them separate for now though, while I play around with some rough positioning. This gives us good height, but I'm going to need to bring the angle around more with another radius piece. Let's pull out the 45 and chuck on a 90 degree 1 1/4. Now we're definitely closer than we were at the start, but I don't want to spend too much time looking for the perfect position on this dummy engine because there's another thing that we need to think about. The K engines are a slant engine, meaning mounted on a slant. I think the actual position is about 20 degrees, but someone can correct me on that, I'm sure. This means that our turbo position needs to take this into account, or our positioning in situ will be wrong. But that's alright, because now we've got our proof of concept, I reckon I can start pulling stuff off the KE70 and mocking it up on the car. Come on. Come on. Fortunately, there's even more space in the KE70 bay than the KE25, so it should be a bit more forgiving to work with. I'm really looking forward to it. It's been a long time in the making. I've had a couple of companies send me out some products to help with the builds that I'm really excited to show you. As I mentioned, those Schedule 40 files that I designed will be up to download on the silver tier of my website, where you can download them for yourself and have a play around with them at home. The adjuster knob that you saw me use on the engine stand and on my press is also up there for free. All you have to do is sign up on the free tier. Let me know what you thought in the comments below and what you might like to see in upcoming videos. I've got a lot that I'm working on, but I'm always happy to adjust for what people want to see. Thanks again for watching. I really appreciate it. See you next time.
Kids barely 6, 17, man, they virgins observant. The pressure put in our seeds to get straight A's. I know I was rushing home just to get straight Blaze. You know the age, naivety, frustration, and rage. Suicide rates constantly raised, and I'm amazed. Graduating, maybe you can work the rest of your life. Education, forcing dreams and aspirations aside. Y'all get the picture. These kids are falling victim to a system, raising money hungry in a food scarce prison. And when that prison is the building blocks for a whole generation, it takes someone great to instigate some separation. Know what I'm saying? So stand alone, fucking stand tall, dog. You can always get up higher than you fall, dog.